Good afternoon, everyone. I'm delighted to have this opportunity to speak with you. We should be grateful for the technology that we have that keeps us all connected and sharing ideas and engaging in how we can improve our industries. So I was asked to talk about logistics and supply chain management by Dr. Alves, and I'd like to take this opportunity to share some of the kind of underlying theoretical concepts and hopefully give you some food for thought as to how this might apply to your projects. I'm the director of the Project Production Systems Laboratory at UC Berkeley. We talk about project production systems because we, of course, are very much interested in the ultimate product of what we design and build. But before that product gets completed, there is a lot of work to be done, as you well know, and that the doing of that work is what we call production. And just like we can design buildings and infrastructure, we can likewise design the production system. So that is being captured with what we call the lean construction triangle. It comprises, of course, commercial terms, the contracts, the incentives that we provide to people to work together on the projects, the organization, the roles we play, the functions we perform, the technologies we use, of course, which serves all the different sides of the triangle. And then at the bottom, we show the operating system. And what we're interested in is what we call the lean operating system. Now, the operating system is kind of something that exists regardless of whether you pay attention to it. It's a bit like the operating system of a computer, right? I mean, we all sit at our computers and we're concerned with Zoom and PowerPoint and those kind of things, but underlying all of that, of course, is an operating system on which the computer runs, and we kind of take it for granted. In many organizations, likewise, we take it for granted that there is an operating system. There are certain rules of behavior and there's certain ways of doing things. But the question is, how good are these rules of behaving and how good are these rules for doing things? And that is what we call the operating system. And as soon as you become aware of that operating system, of course, you will see that there's a huge opportunity to assess its current condition and to perhaps identify opportunities for improvement and drive towards improvement of the operating system. So with that, I'd like to tie this to a framework that you all probably have seen many times before. It's the House of Toyota, as we call it. This is really the lean production operating system that Toyota is using, and there are obviously multiple parts and pieces to them. There are some fundamental principles that we need to adhere to at the bottom: level production, standardization, visual management, and philosophy at large. There are two pillars on the right, the Jidoka, the fact that we want to make quality products. On the left is the just-in-time pillar, the fact that we, of course, want to move forward and deliver our project. And then at the top is the goals. We want to have the best quality, lowest cost, shortest lead time, best safety, and high morale. In the middle, you will recognize people and teamwork is what we call the organization, and efforts related to continuous improvement, and of course, waste reduction. I will focus today on a couple of parts of this House of Toyota in framing what I will be talking about. So let's start with waste production. We already had a very brief snippet from Dr. Alves on as a sampler for today's presentation just a few minutes ago. The 7 wastes in lean production are very familiar to you. Defects, inventory, waiting, overproduction, transport, motion, and extra processing. But what does that mean for our construction industry? Well, here's an example. I went online and I was looking for waste. I was looking for defective materials, and I found this random website, a blog that somebody was writing about their home reconstruction project. And the comment verbatim from the website said something like, well, we're lucky, at least our tile showed up. And thank goodness, only 1 box of tiles that we could tell from just moving them was damaged during shipping. I'm glad I ordered 10% extra of everything. Does that sound familiar to you? Many of you are in procurement. Do we have rules of thumb to order extra of everything just in case? I think it is a very common practice. And unfortunately, it is a reflection of the fact that we have many different kinds of waste in our production systems. As the video also mentioned, I wanted to amplify that these 7 wastes are very much interrelated with one another. So if you have one waste, usually it causes other waste. So for example, if you have poor packaging for the materials, then chances are that some of your tiles are going to break. So you're going to have some actual defects as a result of it. And therefore, you're going to order some extra materials, which now require, of course, extra shipping and extra packaging. And because you risk having some damaged materials, you're going to have to move more boxes than you had anticipated. And at the end of your job, you're probably going to have some extra materials because hopefully you wouldn't need the whole extra 10% that you ordered. And so our systems are really riddled with a lot of waste. And the first thing we need to do is to begin to understand where that waste is. And the second step, of course, is then to go about and removing that waste. So next, I will take you into some systems thinking in the lean supply chains so that you can see how we can begin to approach these concepts of waste management and tie them to lean practices to improve performance. Since we're talking about supply chain management and logistics, I wanted to amplify that a lot of attention is paid, certainly in the academic world, but I think also in the world of practice, on construction and on design, and that perhaps we have not paid enough attention to procurement and materials management. And of course, as this graphic illustrates, it is kind of an absolutely critical link in making the production system work. Now we can investigate these supply systems by looking at different kinds of materials. And the reason for distinguishing materials is that different types of materials will require different practices in regards to how we could procure them and how we manage them. So to give you a few theoretical concepts to mull about, when we talk about products, they can be make to stock. Make to stock means it's all the products that we have readily available on the shelf. They can also be made to order, which means that we're going to have to wait until we know who the customer is. And then when we know who the customer is, we're going to make something specifically for that customer. In make to order, we distinguish engineer to order, where it isn't just about making things, but it's also about engineering the product, designing the product specifically for the customer, which of course takes time. We talk about fabricated to order, where we know already what the components are that we have to make, but we haven't actually made them. And we need to get some raw material and cut it and drill it and bend it to shape to actually make the product that the customer wants. And the last item is what we call assemble to order, where we already have the components made, but we just need to piece them together essentially like a puzzle to make what the customer wants. At the bottom of the slide, you can see a simple depiction of the supply chain. So for all of these materials, we will go from raw materials to the product delivered to the end customer. And the stars on the line are what we call customer order decoupling points. That means the point at which we know who the customer is and at which we can identify the specific requirements for that customer and then tailor the product specifically for the customer's need. So again, on the right-hand side, we have the materials that are made to stock. This is what you get in your supermarket. You basically go, the supermarket has stuff available and you would select items from the shelf and make it your own. Further to the left, we have assemble to order. Obviously, this is going to take a little bit more time to make. It's not so quite readily available. because we have to first understand what it is that the customer wants us to assemble, just like we, assemble a lunch meal or a sandwich. We need to understand what the customer wants and then actually make the product. And so as we move further to the left, you will appreciate that the lead times, the time to actually get the ready product to the customer, the lead time is actually increasing. And the longer the lead time it is, in essence, the potential increases that the customer is going to change their mind. The potential increases that the customer may come up with a different design, may have a different idea, or the potential exists that the owner may find themselves in a different business environment and has different requirements now as to what they need of their facility. And so the longer the lead time is, the more difficult it actually is to achieve what the customer wants, to deliver what the customer wants. And a lot of effort, therefore, in lean construction has to do with reducing the lead time, is shortening the distance between any one of the stars and the right-hand side where the product is being delivered to the customer. So the way we do that is through product design, of course. If we have, for example, very simple components that easily snap together, then it's very fast to assemble a product to order. So we can reduce the lead time through product design. But quite importantly is we can also do it through process design. And that brings us to the left-hand side of the house of Toyota, where we have the just-in-time pillar. The just-in-time pillar, by the way, for some people that is called the go pillar. We want to move forward. The Jidoka pillar is the stop pillar. Stop saying if you make a defective product, you better stop right away. Fix the product, fix the source of the defect so that it will never occur again. Spend your time there so that when you fix the problem, you can then move back to the left to the go pillar, the just-in-time pillar, and move ahead at the greatest speed your production system can. So within the just-in-time pillar, we have a number of methods that we use: takt time planning, pull planning, integrated logistics, and I will highlight two of them in this context. So the first one has to do with the commodity type of materials, the made-to-order type materials that are readily available on the supermarket shelves. Those materials, because they are generic, generally are supplied by manufacturers who will produce the product on forecast. They will anticipate what the customer demand is going to be. They will stock the shelves, and then they will wait for customers to arrive. So the customer or the decoupling point is relatively close to the actual use of the product. And so for those type of materials, because the supply chain is based on forecast, there is a lot of value for suppliers to actually be able to manage that supply chain better. And one way to do that is to have the construction site allow a supplier to come to their site or set up a warehouse very close to their site. So the supplier will have all the materials on hand that could possibly be needed for the construction sites within the context of their product. So the supplier managed inventory, it's sometimes also called vendor managed inventory, really facilitates this handoff between the supply chain and construction. And in a way, if you think about it, there's a pull signal, right, from the construction site. The site will say, okay, 2 weeks from now, these are the products that we need. And the supplier will make them readily available for checkout so that the foreman, the workers that need the materials, will have them readily available at the time that they need them in execution. And of course, there's a lot more detail we can get into here. I don't want to expand too much on it, but my simple graphic, this simple graphic obviously comes with a lot of work that needs to be done in preparation. This is a sketch that highlights on the left-hand side all the work that needs to be done to align the purchasing of commodity materials with what the supplier can provide. And also, of course, the commodity materials will will change over the course of the duration of a project. And so there needs to be some synchronization, some alignment between what the supplier needs to bring to their inventory warehouse versus what the construction site is going to need. So that's what we see on the left-hand side. And then in this example, the supplier would actually set up a trailer system at the location of the construction site. So this is all on the preparation side, on the left-hand side. And then on the right-hand side, we have the execution side. So there's an iteration of weekly consumption of the materials and weekly replenishment. It's really an on-demand, just-in-time type system to replenish what has been consumed and to begin to supply what will be next on the construction schedule in terms of need for materials. So this pull system has huge benefits for the construction site itself because it alleviates the burden of managing these inventories by people in construction, and it delegates it really to the party that's in a better position to manage that inventory, and that is your supplier. And the reason why it's really beneficial to the supplier, of course, is that the supplier probably can reach much further into their supply chain, right? And so as they better understand what the demand is for construction, they can likewise pull from their suppliers and from their manufacturers to replenish the supply chain. And so if you can harness that set of information, you can much streamline the pipeline, so to speak. And in streamlining the pipeline, you can do two things. You can reduce the cycle time, the duration that it takes to get a product to the location where it needs to be. And of course, you can reduce a lot of inventory as well. So our goal in production system design is to think about these pipelines. And I've sketched it here as a pipe, right? So all the materials that are coming towards you, whether it's work in process at the manufacturer or in a warehouse, or whether it's materials in a truck, that is all what we call work in process here. The materials need to come, will take a certain amount of cycle time to get to your location. And then there's a certain throughput rate. The throughput rate is the number of units that will come out of your pipeline per unit of time. That is the handoff that occurs towards construction. This is the handoff where you actually need to find out what the demand rate is of your construction site so you can synchronize the supply with the demand in the system. So that's the goal that we are very much after in production system design. It's to match the supply with the demand. Now here, in this presentation, I only talk about the supply chains. We're not talking specifically about interventions you can do at the construction site to make the demand more predictable, more reliable. But I think many of you who are familiar with lean construction will already have heard about the last planner system, which my colleague Len Ballard developed over the course of many years. And the last planner system, of course, is all about creating stability in the demand so that we can better match the demand to the throughput rate, right? If you want to manage your supply chain, if you want to streamline and have the right materials available at the right time, you have to know what the right time is, and you have to know what the right materials are. And so your construction site, of course, needs to have sufficient level of predictability if you're going to begin to take waste out of your supply chains. The penalties that we pay if we do not try to do that streamlining, of course, is that we pay for it through huge inventories of materials on our construction project, or in warehouses or in different locations up and down the supply chain. And if inventories run out, then of course we pay the penalty of stockouts and shortages, which can be detrimental to our performance at the construction sites. So it's one of these things where the operating system exists, right? Materials do get supplied in one way or the other. The question is more, how much inventory do you need? Where do you need that inventory? And what cycle times, what responsiveness of your supply chain do you need in order to match the demand that you have at the construction site? Okay, so with this example, I talked about commodity materials. So commodity materials, they're generic materials. You can buy them from any one of multiple suppliers. In fact, on large projects, it would not be uncommon to have some redundancy in the system and have several suppliers supply the same product, so that in case somebody runs into problems supplying those materials, that you would have another supplier able to step in to meet the demand of the project. The supply chains for non-commodity material, for the make-to-order materials, of course, are a little bit different because they require the customer to be involved to reach further upstream in the supply chain. And for that, we need to therefore manage these interactions, the interfaces between the design team, the fabrication team, and the contractors, the customers in this case. So the production system design for the more complex products looks more like this. On the right-hand side, we have assemble. Before we get to assembling, we have to deliver materials. When we deliver materials, oftentimes we need to have a combination of many different materials available. We need to have pipes, we need to have pipe supports, we need to have nuts and bolts, for example. So what we try to do in Lean is to alleviate what we call matching problems. Matching problems are problems where you may need multiple components, but you don't have enough of everything in order to be able to put your assembly together. And of course, if you don't have enough, you're going to have to either not do the work, or you're going to do some of the work and then have to come back sometime later. And that may be very punishing in terms of time and in terms of productivity on your project. So if we can buffer, if we can alleviate the matching problem, we should take action to do that. And that is done by means of what we call kitting, is putting multiple parts together. Sometimes it's called bagging and tagging. There's a lot of trade terms for the specific practice, but the idea is you try to make sure that you have all the parts you're going to need before you actually start the work on site. This kitting also can include what we call work packaging. Work packaging is the practice of making sure not just that you have the right materials, but also for engineered to order materials or fabricated to order materials, that you would have the design information together with all the materials, and that you would also have the equipment, reserved, so that you will know, again, that you have everything when it comes to actually doing the work. The parts that are kitted could be both commodity materials, make-to-stock materials, or they could be make-to-order materials. If they're made to order, we may have to fabricate them, which means we have to order the fabrication, which means that if they're engineered to order materials, we probably have to do some detailing on the work. And so further upstream, that means we have to define what we need to detail, and ultimately further to the left, for engineered to order products, we have to design the components as well. And so from a Lean perspective, again, we look at the operating system. The question now comes up as in, what are the questions that we need to ask ourselves so that we can actually streamline the supply system, so that we have the flow that we want, so that we have a short cycle time to get to assembly, and so that we avoid a lot of waste in the production system. And in that regard, there are many, many questions that will come up, starting as early as, what kind of product overall does your owner want to design? But when we break it down to smaller components, the materials that we're actually going to manage in the supply chain, we need to think early on as to whether a product is or is not designed, not just for ultimate use by the customer, but also whether it's designed for fabrication and assembly. In terms of definition, we need to structure the work, right? So the product may be designed for fabrication and assembly, but who is going to perform which task? When are we going to perform these tasks? If we're going to store materials, what kind of inventories, buffers do we want, and where do we want them? Are we going to do the work on site? Are we going to do the work off site? That's what we call part of the definition step. And the detailing step is to think about when exactly the components are going to be needed. Oftentimes, design is done in very large batches based on what's convenient for designers, based on what their software, allows them to do. But the batches, the units of work that define design are very much misaligned with the units of production. You may need to design a whole structural steel system, but when it comes to fabricating steel, you can only fabricate one component at a time. When you order steel, you may go and source your material from multiple suppliers, and so your order batch is going to be different from your design batch, and it's going to be different from your fabrication batch. So when it comes to detailing, we very much want to understand not just what the designer requirements are, but also what the fabrication requirements are, and also, of course, what the installation requirements are, so that we can size the pipeline to match these requirements. In terms of ordering, I already mentioned that we want to reduce the time between the customer order decoupling point and the time that the customer receives the product. So in Lean, we talk about placing orders at the last responsible moment. And as I already mentioned, this has to do with not making products too soon, because we know that there are opportunities perhaps for changing the design or necessities for changing the design. And if we already have fabricated material, those changes become incredibly expensive. So the idea is we like to postpone the start of fabrication for as long as we can possibly responsibly do that. And so the ordering and the fabrication then need to be lined up with the actual requirements of installation at the construction site. And here again is where a lot of work packaging work needs to be done in production system design. It's figuring out what are the construction work packages, what are the installation work packages, what are the engineering work packages, and line them all up. After we get to fabrication, I already mentioned the need for kitting to help alleviate the matching problem on site. But the question is, where are you going to do the kitting? And are you going to have multiple kits that ultimately get put together in a bigger kit? Or will we have small kits and then still have some kind of a matching problem left further downstream in the supply chain? Then we get to delivering. Of course, can we deliver just in time? What does just in time mean? Obviously, we don't want to be just late. Do we do it in work packages? Can we actually size the delivery to match with the handling on site? We'd like to do one-piece handling. Unfortunately, many components get handled not just once or twice, but maybe 9 or 10 times. And so there's a lot of waste that we can possibly eliminate through better planning and through better production system design. So these are all the questions for you to maybe ponder on the projects that you are managing. And from a Lean perspective, I think a couple of key questions further needs to be asked. One is, have we identified where all the variability is in our system? And have we eliminated all the unwanted variability? So some variability is good, right? So if you design a piping system, it makes sense to have pipe of different diameters because there are different functional requirements to be met. And obviously that is good variability in our system. But if the variability is not intentionally wanted, if it's not explicitly stated that there's value in that variability, then we talk about bad variability. And obviously bad variability by definition needs to be eradicated. So we need to spend time trying to eliminate as much of that as we can. For any variability that remains at that point, because it takes time to reduce variability, for any variability that remains, then the question is, well, what kind of buffers are we going to use? Will it be time buffers? Will it be space buffers and inventory? Or will it be capacity buffers? And where are we going to put those buffers in our production systems? And then can we size them? Can we make them large enough so they can actually take the blow, so to speak, when that variability manifests itself, take the blow so that we wouldn't have a detrimental impact on performance on our assembly processes on our construction sites. Key design criteria are to design assembly operations collaboratively, to safety, quality, time, and cost criteria. And then, of course, as a production system, we would like products to flow to the extent we can. So how are we going to design continuous flow systems, right? Where can we actually implement pull as opposed to push? And can we take the pull maybe a step further and make it into a continuous flow process where we truly have smooth continuation with very little inventory in the system. So what does that look like for our engineer to order product? Think of reinforcing bar cages as engineer to order product. So the production system design will have, you know, all these different steps. I have not illustrated them here one by one, but the idea is in the upper left that you would have some collaborative planning where people bring expertise from different parts in the supply chain together. So not just structural engineers, not just designers, but also fabricators, and also the rod busters, also the iron workers on site probably have very good insights into what is easy to build, what is hard to build, how injuries occur, and what they can do to prevent them. And sometimes it's a matter of adding perhaps a couple of pieces of rebar to prevent that people would get their fingers hurt on site. A couple of rebar pieces are not going to cost a lot of money, but they really improve the product and the process for installing that product. Obviously, there's a lot of information technology nowadays that we are so fortunate to have that can help us with reaching shared understanding, capturing the details, capturing the lessons learned from all these different perspectives. And then we have very good tracking technologies also that can help us know exactly where inventory is in the pipeline, whether materials are coming or not coming, and whether they have been installed. And so with these technologies in place, we have a good sense as to where things are, right? We know the pipeline quite well. And if we know the pipeline quite well, a technology that we can apply, a method that we can apply is what we call the CONWIP system. So CONWIP is a kind of pull system, as you can see it. It's a similar area to what I showed you before, where we had pull in vendor managed inventory. But here the CONWIP starts from the construction sites and reaches all the way back into the design part. And in between is essentially a pipeline. And we want to streamline that pipeline. We want product to flow through that pipeline as efficiently as possible. And at the same time, we don't want the pipeline to burst because there's too much inventory in it. And so a lot of supply chain management work for engineer to order products and focuses on identifying the right batch sizes for installation and understanding installation rates, understanding demand rates at a construction site, and then feeding that information back up to the start of the pipeline. And the idea of CONWIP is that if you can properly size the quantity of material that you allow to enter into the pipeline, then in the pipeline itself, everything will continue to flow. And you will get product out at the rate that you need to get it out in order to satisfy the construction needs. I mentioned CONWIP because it is a kind of pull mechanism. So, you know, I hope you already appreciate all the benefits of having pull in a system. What's nice about CONWIP is that it is actually much simpler. In the supply chain management example that I gave you before, the supplier managed inventory example I gave you before, we had multiple pull signals, one after the other, to help streamline the supply chain. That is useful and it's helpful, but it comes at a cost, of course. The cost is you have multiple pull signals. And you can have many in many different directions in any kind of production system. What's elegant about CONWIP is that it just controls the release of materials into the pipeline. And in fact, that single signal already achieves many of the benefits that you can achieve by using pull signals. And obviously CONWIP is much simpler to implement because it's only one one buffer that you have to size. It's the number of units that you're going to allow to enter into your production system. So this is a very useful technique to help synchronize the release of design information to detailing and fabrication and transportation to match the demands for materials at construction sites. And so that brings us back then to kind of the house of Toyota, right? And the examples I provided have illustrated how we can do logistics and supply chain management using many of these principles that are in the house of Toyota. There are, of course, many other principles that will need to be implemented kind of hand in hand with those, because, for example, for a product to flow, we need to make sure that the product that flows through our pipeline is going to be a quality product, that there are not going to be defects. We cannot afford to synchronize the system with supply to match demand if supply is actually going to produce defective products, right? Then we're back to square one with our box of tiles, where we have to order more tile because our supply chain cannot be perfect. And in Lean, we always strive for perfection. So while we're lining up the supply chain, at the same time, we have to work in the other elements of the house of Toyota. We have to work on the Yudoka pillar, build in mistake proofing, build in redundancy perhaps in designs to make sure that we can achieve quality, do root cause analysis if we run into problems, and perhaps do, you know, quality control in many more locations than we traditionally have, again, to prevent that we pass defective product to anyone else in the supply system. So that is my presentation. I wanted to allow a little time for question and answer. I hope you have some questions about the concepts that I've introduced. So I'm all ear.
I think we can postpone the questions until the end.
Oh, if you like, of course. Sure, that's fine. Whichever you want to do.
Okay.
Then I'll just pass the baton.
Thank you so much for the presentation. It's very nice. Thank you so much, Professor Tommelein.
You're very welcome.
Now with our second presenter, Dr. Thais Alves obtained her PhD degree at University of California, Berkeley, under the supervision of Dr. Iris Tommelein back in 2005. Dr. Alves specializes in construction management and project-based production systems, including the use of lean production, construction concepts, principles, and tools to improve the performance of production systems and how people organize, collaborate, and learn from planning and scheduling activities. She is currently the AGC Paul Astrowell Chair in the Construction Engineering and Management at San Diego State University in California. You can start now.
Thank you, Dalvat. Thank you, Dr. Luisa Beck, for the invitation for this presentation with Professor Iris Tommelein. So my goal here today is just to introduce the International Group for Lean Construction. I'm the IGLC Secretary General this year, and this is by no means a definitive description of what the IGLC is, but at least it gives you an idea of what the group is and how we work in general terms. So next slide, please. So the IGLC vision is posted on the IGLC.net website, which is the house of the IGLC group. So the goal of the group is to actually meet customer demands to dramatically improve the architecture, engineering, and construction industry. So the goal of this group is to change the industry. We have done lots of things over the past almost 30 years. We are going for IGLC 28 now that Professor Tommelein is hosting virtually from UC Berkeley. And the goal is to develop new principles and methods for product development, production management that are tailored to our industry. So while we look after we look for new ways to doing things from other industries, we want to adapt them to construction, and we want to make it work for construction. So the IGLC is based on this premise. Next, please. So a little bit of the IGLC history so that you can understand how this organization actually started. In 1992, Professor Lauri Koskela, he published the application of the new production philosophy to construction. And this is the lean construction start. This is the seminal paper of lean construction. And that's where the term was coined. And this report is incredibly relevant to this day. So we are over 25 years down the road. We celebrated that a few years ago. And this report is still extremely relevant. If you haven't seen it, I strongly recommend. I use the principles outlined in this report in my classes, and I use to view the world. I use these principles to view systems in construction and how they are organized. So in 1993, Professor Lauri Koskela organized the first IGLC in Finland. At the time, he was at the VTT in Finland, so he hosts the first one. The second one, you see, moves on all the way to Chile in 94. In 95, Greg Howell and Glenn Ballard, they organized here in US, in Albuquerque, New Mexico. So at the time, Greg Howell, which we missed last week, and he was such a force driving the IGLC throughout these almost 30 years. And Glenn was in Berkeley at that time, and they hosted the event in New Mexico. So you see there that the foundations were established in these first three events, and a rotation starts. So the IGLC, we move around the globe every year. So you see the event was in Europe, then in South America, then in North America. So there is a rotation because we want to go to different places and give people a chance to participate in a closer geographical location. Now we are going virtually because of the circumstances. So the next one, please. So this is directly from the IGLC website and from the charter. So the annual conferences, they are the main activity of the IGLC. The IGLC doesn't exist as a formal organization, except for our presence online and the fact that we are a network of people who have the interest in advancing lean construction in our industry. So the main activity of the group is the conference. It rotates amongst the continents, as I mentioned. Over the year, we meet, a number of us meet for different reasons in events, or we start study groups and we try to advance our own teaching and research. And the idea is that locations and places and organizations that want to host the conference, they make a proposal 2 years in advance. This is presented to the IGLC community. And the participants of a business meeting, which we host every year during the conference, they have a chance to vote and choose the next destination. And we follow the rotation to the extent possible. So this year, as I mentioned, Professor Tommelein is hosting it virtually because we cannot meet in person. It was scheduled to be in Peru, in Cusco, Peru. And that was postponed to next year. And in 2 years from now, Professor Farouk Hamzeh is going to host in Canada. So this is how we operate with the annual conference. Next. Here, it's just to give you an idea, and I strongly recommend if you have a chance to browse these papers and these conferences in the IGLC.net website. One amazing thing about the IGLC is that all the knowledge that we have generated over these years, they are pretty much in a single place, except for the first 3 conferences, which were put on a book, and you can also get the book. But if you go to the IGLC.net and you go, you are going to see all these conferences and the variety of places that we have been while these conferences hosted. You click in any of these, you are going to be able to see the papers. They are free to be downloaded. And there is a range of papers from very theoretical foundational papers all the way through very hands-on implementation-driven papers written by practitioners and or practitioners in collaboration with academics. And of course, the bulk of it is us researchers, academics driving research. So I strongly recommend that you take a minute to check this website and take some more time to explore. And there is a search feature that you actually see here, and you can type last planner system or supply chain management, or you can type Professor Tommelein's name, and you are going to see all the papers associated with that. And they are very well organized every year by, we have sections that we covered in the IGLC, and I can guarantee you any topic that you might be thinking about exploring, whether safety, supply chain management, production system design, last planner system implementation, I strongly recommend that you start there, because there is a host of papers and knowledge that you can build upon. And we also have some presentations also posted for your use. So next. Here is just to let you know how the IGLC actually works. So the International Group for Lean Construction is truly international. Yes, some countries, they tend to drive a little bit more of the publication, but what you see here is a host of countries with participants, researchers, practitioners doing research. And this just gives an idea of where we are and the different locations where research has been done and different affiliations of the folks. So we have a pretty broad coverage as far as the Americas go. We have strong presence in Europe. We have presence in Asia, Middle East, and Oceania. So we want to expand that, and we need your participation too. So maybe in a few years, or maybe next year, you might be writing papers about your own experiences and having a chance to share with the group and discuss. Next, please. So finally, the IGLC is a network. As I said, we don't exist formally except for our website and the fact that these conferences are hosted. We are a network. We respect people. It's a major principle in the lean construction, the lean production philosophy, if you will. And we respect each other. Every year we see people who are starting on their lean journeys, and they come to present and they get feedback, and they make new friendships, and they grow in their journey, and they move on. So the group is extremely welcoming of people who are in different levels of their understanding of lean. So I strongly encourage you to join us for the conference that Professor Tommelein is organizing this year. You will see that it's an environment that is inviting. We like to engage in discussions, and we are an incredible, amazingly put together, or it's a group that we like to be with each other. We like to challenge each other. We like to drive research and practice, and we are there to help each other. So that's basically a strong point. So in the next slide, we actually see a number of us. This is by no means comprehensive and definitive, but these are folks who are in the IGLC and have hosted events. We have edited proceedings. We have been reviewers of previous conferences. We have published papers. So all of us in this picture, we have been actively engaged in making the IGLC a better and more comprehensive and more accessible organization. Some of the folks in these pictures are not with us anymore, like Greg and Sven Bertelsen, but we owe them for keeping us moving and for their enthusiasm, and we have to carry on. So this is us, and there are many of us who are not in this picture, but I just wanted to give you an idea that IGLC is a network. We respect people, we respect diversity of thinking, of approaches and methods, and we want to be literally all over the globe because everybody has a different experience and different strengths. So my last slide is actually an invitation to all of you to go to IGLC.net, have a chance to familiarize yourself with what is on the website, take some time to browse the papers, find something that is interesting for you or for your organization, and don't reinvent the wheel, right? Build on the shoulders of people who have already worked on these things, and they might be able to open your eyes to new areas and help you improve in your lean journey. So with that, I would like to thank Dr. Liza Elsbeck again for the invitation, and I'm available for questions if there are any. Thank you.